Okay, so this is another video about multiple testing. I just wanted to start by noting that I've rearranged some of the material on the syllabus page. So all the stuff we covered last time is under lecture 12A here, and then some of it is the stuff we covered last time on multiple testing, like Q-value, and the empirical Bayes approach to multiple testing, which I covered in lecture. I've moved in with the other material on multiple testing. So if you go here, you'll see there's actually the video from last lecture is included. And if you didn't attend lecture, I recommend you watch it because we did cover some material there. And I will add this video once I've made it to this page on multiple testing. Okay, and it's this video is going to be going over these notes here, the PDF. Well, actually just kind of, when I say going over, highlighting the important parts. So I've got that PDF open here. So you should read it, but the main thing I want to emphasize in this video is the material on the family-wise error rate and the false discovery rate as defined, formally defined in a frequentist point of view, because that's kind of the non-Bayesian point of view, where the truth or falsity of the hypotheses is fixed, and you think of the test statistics, which here we're going to call T here. They're the data, they're random, and you look at the behavior of procedures over repetitions of collecting T, new T. So all the randomness here is going to be in terms of T, whereas in the Bayesian paradigm, the hypotheses, we often end up computing the probability the hypotheses are true or not. We talked about the local false discovery rate last time. So you think of the hypotheses as being uncertain, and so having probability associated with them. And the frequentist point of view, you instead think of the hypotheses as being fixed and the T's as being random, and you study the behavior of procedures under random sampling of the T's. Okay, so the key table is here. It's a very simple idea, is that when you're testing a large number of hypotheses, in this case M, so that's the total number of hypotheses, you'll accept some and you'll reject some. So the total number of rejections is R and the total number of acceptances is W here. And some of the ones you accept will be true nulls and others will be alternatives. And some of the ones you reject will be true nulls and some will be alternatives. So when you accept, or let's say when you reject the null hypothesis and the alternative is true, this is good. So S is good. If you accept the null hypothesis, or maybe I should say don't reject the null hypothesis and the null is true, then that's good. And then the mistakes are the V and the T. So here, these numbers here represent the number of hypotheses you reject when you apply a given rule. Okay, so V is the number. And so that will depend on the rule, of course, but also given the rule, it will depend on the test statistics you see. Okay, so the T's. So V will be random because it depends on the T, which are random. Okay. So if we knew all these quantities, we would compute the false discovery rate, or what some people call the false discovery proportion, FDP, to the rate. We'll see in a minute what the rate is defined as. So the false discovery proportion is the proportion of things that you reject, that is R, that are false discoveries. So that's V. These are false discoveries where you reject and they're actually true nulls. So they're false discoveries over R. Yeah. So V over R is the false discovery proportion, and then the false discovery rate is just defined as the expectation of V over R. So that's sorry, let's see. Here we go. Okay, but we have one extra wrinkle here. is that R can be 0. And so what do you do if R is 0? Well, of course, if R is 0, V is 0 as well, because R is the number of rejections and V is the number of rejections that are false. So the idea is if you make no discoveries, we're going to define the FDP as 0, right? If you make no discoveries, there are no false ones out of your no discoveries. So we're going to define the FDP as 0. And so the FDR is the expected value of the FDR of V over R, given that R is bigger than 0 times the probability that R is bigger than 0. So one of the funny things about this FDR is that you really want this to be big, right? You want to reject things. Okay. So you want this probability to be big, and it's this quantity you want to be small. The expected proportion of false discoveries given that you make some discoveries. So you want this to be big and this to be small. And so, Story, motivated by that, defined this quantity he called the positive false discovery rate, which is this part here. But the problem with the positive false discovery rate is that you can't control it in the frequentist sense. That is, you can't have procedures that guarantee, in general anyway, that this is less than some threshold. And that's because you can just take the case where every null is true, the global null, that's here. When all the nulls are true, the false discovery proportion is always 1, whatever your method, unless it always rejects everything. Well, and then it's undefined because R is never greater than 0. Sorry, always rejects nothing, unless R is always equal to 0. So because of that, because the initial, at least, and usually when people talk about controlling the FDR, they're controlling this quantity rather than this quantity, even though you might want this to be big and this to be small. Okay, so that's the false discovery rate. I also, in this text, define the family-wise error rate. So that's of less interest, but still also useful to know about because people will talk about it. The family-wise error rate is defined here, is the probability that even a single null hypothesis is wrongly rejected. That is, that you reject anyone, that you make any false discoveries. The probability, in other words, it's the probability that V is bigger than or equal to 1, because remember that V was the number of false discoveries. Okay. So the family-wise, really the innovation of the FDR when it was introduced by Benjamin and Hochberg, the innovation is that it recognizes that it's a mistake to worry too much about rejecting even one null hypothesis wrongly if the majority that you reject are correct. Because why is it a mistake? Because it leads to procedures that are too conservative. If you really try to, the idea is that if you really try to reduce your probability of rejecting even one wrongly to a very small value, you just don't find anything in most cases, or in many cases, you don't find many things. And that's because the family-wise error rate is essentially a too stringent criteria, right? Trying to make no mistakes whatsoever is too strong when you're looking at this kind of setting. What you really want is that you find lots of things and most of them are right. Not 100%, but most of them. So they think of the FDR as a kind of a relaxation, a less conservative criteria than family-wise error rate. Okay, so it's also in some ways a more meaningful error measure rather. Most scientists, what they want is a collection of findings, most of which are real. They don't want a small collection of findings, all of which are guaranteed to be real, or high probability of being real. Okay, so so that's what the family-wise error rate and the false discovery rate are definition, and the simplest approaches to controlling those two error rates, which means developing procedures that can guarantee that these error rates, or at least these expected error rates, are less than some threshold, let's say alpha, are called the Bonferroni procedure and the Benjamini-Hochberg procedure. And both of them are super simple. Sorry, this is controlling the FDR, controlling the family-wise error rate here in section 3. So essentially the Bonferroni procedure, here it is here. Sorry. Yeah. Okay, my screen share seems to have stopped. So yes, as I was saying, the simple approach to controlling the family-wise error rate is the Bonferroni procedure. And so you can read it through here, but the key here is this idea here is that you control the family-wise error rate. That's the probability of making even one false discovery. But at level alpha, which think of alpha as 0.05, for example, for now, by controlling each of the m individual tests at level alpha over m. So if you did 1,000 tests and you want to control the family-wise error rate at level 0.05, then you would control the individual tests at 0.05 divided by 1,000. That is if the so if the test statistics are p-values, then you would reject if p is less than not 0.05 but 0.05 divided by 1,000. And the procedure is a conservative procedure, which means that the family-wise error rate under this procedure is guaranteed to be less than alpha. Okay. At least, yes. So that at least weak control, and if they're independent, if the tests are independent, you get strong control. So you'll have to see the details to see what the difference is between weak control and strong control. Okay, so the problem with the Bonferroni, as we've said, the family-wise error rate is a very stringent procedure. So the Bonferroni procedure tends to not result in many discoveries. So that's what motivated people to develop the false discovery rate. And the Benjamini-Hochberg procedure is guaranteed to control the false discovery rate, assuming that the tests are independent. In practice, actually, it works really pretty well even under dependence. And there are some theoretical proofs that it works under certain types of dependence. But in fact, it seems to be pretty robust empirically. And so here's the procedure, just to emphasize it. You take your p-values from all your tests, let's assume they're p-values for simplicity, and you rank them, okay, from smallest to largest. And then you compare the smallest one to alpha over m, and you compare the second smallest one to 2 alpha over m, and you compare the third smallest one to 3 alpha over m, etc. And you reject as many hypotheses as you can, such that pi is less than or equal to I alpha over m. Actually, there are two procedures in common use: a step-up procedure and a step-down procedure. One of which kind of only rejects the first k tests if all of the p-values pk are significant by this kind of comparison. Another of which rejects the largest k, and they're both guaranteed to control the FDR. One is less conservative than the other. But anyway, so think of this. This is, you just take the largest k for which your p-value is less, your ith biggest p-value is less than or equal to I alpha over m. Largest k for which pk is less than or equal to k alpha over m. Okay, so you can see that that's if the first one, the smallest one, is significant in the Bonferroni procedure, that's what the first one you're comparing with alpha over m. So if there's something is rejected by the Bonferroni, then you'll also have something rejected by the Benjamini Hochberg. But as I increases, the threshold that you're comparing against becomes less stringent, and that reflects the fact that the FDR is a less stringent error rate than the family-wise error rate is. Okay. So very simple, two very simple controlling procedures. You should definitely make sure you're familiar with both of them. Okay.